Um, Hello, everyone. My name is Qinghui Liu. English name is Brian. I'm from Norwegian Computer Center and also the UiT Machine Learning Group. So today I'm very happy to present our work at SCG-Net, safe constructing graph neural networks for semantic segmentation. So this is joint work with Michael and Robert and Arnberg. They are also from UiT Machine Learning Group and Norwegian Computer Center. So generally, this talk would include 4 parts. First, I will give a short talk about the motivation behind this work, and then I will describe the details about our main idea. And then I show some evaluation results. And finally, we draw our conclusion. We'll try our best to make it quick as possible. So firstly, the motivation about this work, because you may know the traditional segmentation models are heavily rely on the deep convolution networks. However, these convolution kernels have natural limitations. It's local receptive fields. So that means that a convolution kernel is not so good at modeling the long dependencies. So that if you want to model long dependencies to capture global informations, you have to stack as deep as possible many convolutional networks, such as the below 2 very famous models, the UNet and the SCG-Net. They stack a lot of convolutions and pooling, max frames, this kind of layers, both on the encode part and decode part. This way is, from my point of view, it's not so efficient to do this. So we want to build a more efficient way to capture the non-local context informations. But we at this time we want to also recently years the graph neural networks has proved a very powerful model to capture global context information. So once you have graph structure available, such as in some programs in domain of social networks and chemistry, something like that, it's a powerful tool to because graph neural networks is naturally to can get the global informations. Here is a very famous variation of graph neural networks. It's called GCN graph convolution networks, which was introduced by the Keith and Werling at 2016. But generally, the model can be broken into 2 steps. One step is called neighborhood aggregation. The second step is called feature updating with neural networks. But this way, you only have one layer can effectively to aggregate global representations. It's very effective. So, but how to adopt, how to exploit the graph models into the computer vision? Because in computer vision images, you don't have the graph structure. So, and it's also not impossible to build a graph matrix manually. So based on this, we introduced a very novel structure to automatically to learn latent graphs. It don't rely on any prior knowledges. So this figure shows some overall structure of the proposed models. And basically this structure is based on the traditional variational autoencoder structure. If you have some experience with these VAE models, it could be easier to follow the structure. So here I just give a very brief introduction about the model. So firstly, the overall structure consists of two parts. One part is called encoding part. Here, the encoding part, in the encoding part, they just learn a mean matrix here. And with the standard deviation matrix. By this way, we use the reparameter tricks to get the so-called latent space, that. So by this way, we decode the latent space to measure the similarities between each nodes. So essentially, the decode part just is kind of give the to generate the latent graph to present the some such as the semantic similarity or feature similarity between the nodes, such that the similarity regions can exchange informations by the following the graph models. So by and also we also introduced two regularization terms to guide the learning process, to make the learning process more smoothly. And we also introduced one residue terms defined as here to can fuse together with the final prediction from the graph models. By this way, we can refine the final predictions. So this is the overall the structure, the main idea. So based on the proposed the SCG module, we developed the end-to-end segmentation models. Here is the details about structures. So here we use traditional convolution backbones to generate the feature maps. Then we pass the feature maps, two different maps to the SCG modules. Then the SCG module will automatically correct the adjustment matrix and some embedding and the embedding features with the residue and regularization terms together, and pass it to the two layers graph neural networks. Finally, the final layer of graph networks will predict the classes. So C here means the number of the problem, the number of class of depends on what's your data set. So this is overall structure is quite clear and simple. So we evaluated our proposed method on the benchmark data sets from a remote sensing community. Maybe you heard about it. One is the Potsdam dataset, another one is the Wahhagen dataset. Both we use only 3 channels. For the Potsdam, we use RGB, and for the Wahhagen, we use the IRG channels. They have different resolutions. For the Potsdam, they have 6,000 times 6,000 fixed resolutions for each images, and it contains 24 training patches and with 14 images as test on system. And for the Wahhagen, they have 16 images and with 17 as the test. So here's some examples about the input image and the ground truth. So we have different color represent different classes as shown in the above. So firstly, we evaluated the computational cost. So we compare on the validation dataset, we compared with some popular convolution networks like UNet, FSIN, and SCG-Net, GCN, something like that. Here is some numbers about the parameter size and computational costs with measured by F-loops. And we also computed the inference time on the GPU and CPU both. And we found that our model is quite efficient, both on inference time and with the training and final performance. So it's very impressive. And finally, we evaluated our models on the holdout test set. First, this table shows the post-time results. And also we compared with all other published models based on the same test set. So still our model achieves very competitive results with some other results. And also we use exactly the same models to vehicle test set. So similarly, this model also achieved very, very close the standard of the results. So these results just show that our method can give a very good prediction on the semantic labels. Here is some visualization about the final mapping predictions. The quality is quite high compared with some other benchmark models. However, we also find some small problems here that the graph models here is a little bit blurring to detect the boundary of small objects like the cars. So this can be a future work. We will investigate more how to improve it. And we also did some ablation studies. First, we visualized the learned graphs. So from these figures, we show that the proposed model can successfully to generate some latent graphs. And so that's, we believe that there's a reason why the graph network can predict so well on the final segmentation results. And we also did some other ablation studies to evaluate the effectiveness about the proposed, such as the regularization terms and residue terms. So basically, if we, for example, if remove the residue and the regularization, so the learning process can be very slow, and we take 4 times longer times to get the local optimal results. So, and also some other, we also test this with different input size and node size. And finally, we see with the 448 times 448 input size with this node size can achieve the most, the best results, and in terms of very fast inference speed. So to sum up, basically here we proposed a novel structure, so-called self-constructing graph framework. This can learn the hidden graphs directly from the 2D feature maps without any prior graphs available. And we developed an end-to-end model based on the proposed modules, which achieves very competitive results on the remote sensing dataset, but confuse very few parameters and computation cost. So, and also the proposed model can be easily to extend and adapt it into existing convolution networks and graph network together. And yeah, basically that's our work, and thank you very much for your attention.